Hi everyone, welcome to our last lesson in 6.3. We're looking at domain and range still, but this is part 3, and in our notes it is called set notation. It's a new section in our notes. We're going to learn the last way to describe the domain and range, which is using a little bit different a different set of brackets. It's a different way to describe the domain and range, but it's very similar to what we've looked at already. So set notation, I'm just going to go ahead and we've just finished interval notation, so I'm just going to get you to cross this out of your notes. We don't really need to go over it again. So we remember that when we use interval notation, we use a set of brackets, round brackets or square brackets, and we show the upper and lower limit. That's interval notation. Set notation is a little bit different, and set notation is very similar to interval notation. It still shows the upper and lower limits in brackets, except we use different brackets. And this method also shows whether the values for x and y are integers, real numbers, or natural numbers, okay, or whole numbers, etc. So it will describe whether we're talking about continuous data or discrete data. So this is the best method for domain and range because it gives the most information. And it's the one you're going to use in Math 11 and Math 12 as well. We use curly brackets for set notation, just like we did for a list. So curly brackets look like this. Okay, that represents a set. And let's go ahead and before we do some examples, let's define a few terms that we need to know. So here's some symbols that we need to know. The first one is this funny looking E, and it means belongs to or is a member of. So is a member of a particular group of numbers, okay, or belongs to. So for example, we're going to have, I'll put an example to the side here. X is a member of the real numbers. So X, and then that funny looking E means X is a member of the real numbers. So we're going to link X or Y with a group of numbers to say whether it's continuous data or discrete data. The other thing we're going to use is a long vertical line, okay? And this means such that. Okay, so we'll go ahead and I'll show you how we use these in a moment. Okay, the other symbols that we have to use are these less than or greater than symbols. And you might remember these from, a long time ago in math. And when you're looking at a symbol, I'll do a big one down here like this. Okay, the point points to the smaller value, and the big mouth points to the bigger value. So it's always pointing to the smaller value. Okay, and sometimes back in elementary school, you think of it like a fish, and the big mouth of the fish is eating the bigger number. Okay, so this is true. So if we're reading it from left to right, it means that whatever number is on the left here, okay, is greater than. So this is the greater than sign. And it's called a strict inequality because if we don't put a little line underneath it, it means that that value is not a possible value. So it's, for example, x is greater than 1 means that 1 would be an open data point, greater than. So it can be bigger than 1 but not equal to 1. If we have the possibility of a limit being included, we put a little equal sign or half of an equal sign underneath. And then that here means greater than or equal to. So that's when a point is included. We would use that. If the point is going towards the left, that tells me that's less than. Okay, that's sort of the generic less than sign. And if there's a little line under it, it means less than or equal to. And we're going to practice with these. So don't worry. Okay, let me just quickly show you then just a quick example right here. Okay, and any inequality, okay, can be written two ways. So, for example, let's say that in words x is greater than 7. Okay, say that's what we have in words. X is greater than 7. You can write that two ways. You can say X, okay, is greater than, so we're going to put the big mouth towards the X, and it's pointing to the smaller number, which is 7, like that. X is greater than 7. This is true. This is saying the same thing. 7 is smaller than the X. I could also write that the other way. So it's also totally fine to say X over here on the left, on the right, is greater than 7. Okay, so it could be written both ways. This can also be read as 7 is less than X, which is true. Okay, so you can read this left to right. So these signs are just to help you understand them and remember them, but you can actually use them. You can flip them in both directions as long as you put the bigger number with the big mouth. Okay, and the smaller number, okay, goes on the smaller side, or where the inequality is pointing towards. So both of those are totally acceptable. Okay. Also, we have to know how to, we're going to use a symbol, a capital letter, to represent real numbers, integers, natural numbers, and whole numbers. So the types of numbers that we have dealt with so far are the real numbers, which is all different types of numbers. And we use capital R here for real numbers. Okay. So if we want to say that data is continuous, we'll say that all real numbers. In words, we'd say all real numbers. But now in set notation, we'll use a capital R. Integers, we use capital I to describe all the values of x or y as integers. If x and y can only be natural numbers, and remember natural numbers on your real number sheet include 1, 2, and 3. The counting numbers greater than 0, those are natural numbers. We use a capital N to show natural numbers when we're describing the values. And whole numbers, we use capital W. And whole numbers are when you have 0, 1, 2, 3, on and on and on. So they're only positive ones. Okay. And so we use a W to represent whole numbers. We aren't going to use these ones here, rational numbers and irrational numbers. Just for your knowledge, rational numbers are shown as a Q with a line under it, and irrational numbers are a Q, but we don't need to know these, okay? We do need to know these. We need to know these only. Okay, so real numbers, integers, natural numbers, and whole numbers. And remember that integers, natural numbers, and whole numbers are all discrete. These are all discrete data, types of discrete data. Okay, let's go ahead and do some real examples here, putting it all together. So, how to write set notation. Okay, you're going to again write two sets of brackets, one's for the domain and one's for the range, and you start it off like this. Okay, if we look at it, we have a curly bracket here and a curly bracket at the end. And what we're going to say is x, I'm going to write it up above here too. X is such that, so we put the x here first, that just tells us we're talking about the domain. Okay, by putting an x there. So x is basically such that, and then we're going to put the upper and lower limits of x. And we put the lower limit first. So this would be our lower limit. So for example, let's just say it's 10. Okay. Then we put an x in the middle. Okay, and we want to say that x is greater than our lower limit. So we say x is greater than 10, okay, or if it's equal to 10, we'll use the correct sign here, but this is just an example. Okay, and then we would say it's less than the upper limit. Let's say the upper limit is 20. Okay, so we show the lower limit to the left of x and the upper limit to the right above it, and we use the correct signs there to show less than, so greater than, lower limit, and less than the upper limit. Okay, so that just tells us the lower and the upper limits. Then we use a comma and we say x is a member of, and then whatever kind of numbers x is. So if x is all real numbers, it's continuous, it's a connected line, we use a capital R. And then we close it with a curly bracket. Okay, and then we do the same thing for the range, except we use a y instead of an x, everywhere that you see an x. Let's go ahead and do some real examples. So we have, this is our first example. The domain is all real numbers. So the first thing I do here is recognize that this tells me this is continuous data. And I'm going to, that right away tells me that I'm going to write x is a member of capital R, the real numbers, at the end of my set notation. Okay, I know I'm talking about x because I'm talking about the domain. Okay, and here's my limits. It's between 0 and 10 inclusive. So this is my lower limit. And 10 is my upper limit. And inclusive is important because that tells me that x can be equal to 0 and x can be equal to 10. Okay, so that tells me those are solid data points if I was looking at a number line or a graph. So let's go ahead and do my set notation. So the domain looks like this. We use a curly bracket and we say x is such that, I'm going to put my lower limit first, so x is, okay, greater than 0. So I'm going to write a greater than sign here. X is greater than 0. It can also be equal to 0. So I'm going to write a little half of an equal sign under there. So that says x is greater than or equal to 0. Okay. And I know that it can be equal to because those points are included. Okay. My upper limit is 10. And x is less than or equal to 10. So it goes all the way up to 10. So I'm going to use this sign right here, which is telling me, this is telling me that x is less than, okay, or equal to 10. Okay. Finally, the last thing I have to say here is that x, this is continuous data, x is a member of capital R, the real numbers. And I close the brackets. Okay, let's do another example for y here. So the range tells me I'm talking about y. So right away I can start off by using a curly bracket, okay, and saying that y is such that, well, what's the limits for y? Let's have a look. All real numbers, so I'm talking about continuous data, between 0 and 20 inclusive. So it goes from 0, solid dot is 0, to 20. Okay, and 0 and 20 are included. So what I do here is I'm going to say 0 is my lower limit, and y is greater than or equal to 0, and less than or equal to 20, comma, y is a member of the real numbers, close the bracket. These just take a little bit of practice, okay? Let's do a few more together. Okay, let's have a look at a number line and then a couple of graphs here. So let's look at this number line. Let's say that the domain is given to you like this. Okay, I want you to put a solid dot at -4. Okay, solid dot, and a solid dot at +5, and connect them. Okay, so -4 to +5. That's the domain. How would I write this in set notation? Okay, I would use curly brackets. I know I'm talking about the domain, so it's x. I say x is such that, well, what's the lower limit? The lower limit is -4, okay, and it's included, meaning that x can be equal to -4, and it goes up to +5, and +5 is included. So x is greater than or equal to -4 and less than or equal to +5. So -4 is my lower limit, and x is greater than or equal to that, and it's less than or equal to the upper limit 5. Comma, what kind of numbers is x? Well, if you look at your number line, they're all connected, which tells you that we have continuous data. So when I have continuous data, all my numbers are connected by a line. That tells me that these are real numbers. It can be any real numbers in between -4 and 5. So we say x is a member of the real numbers. Close it with a curly bracket. Okay, let's do another one that's a little different here. So let's do the range below. And let's start again at -4, but we're going to use an open circle. And I want you to put a continuous line with an arrow going in the positive direction. Let's write, this is a number line showing the range, which tells me I'm talking about the y values, the possible y values. So let's go ahead and write our answer. It's going to be curly bracket, y is such that, well, what's our lower limit? Our lower limit is -4, and it is not included. Okay, and the upper limit is infinity, so there's no upper limit. Okay, so I'm going to start with my lower limit, which is -4, and I put it first. And I want to say that y is, well, what is y? Is it greater than -4 or greater than or equal to -4? Well, I can see that it's not equal. It's not equal to -4. So I'm going to just have a greater than sign. Okay, this is really important. So this tells me that it is not equal to -4. It's just greater than. Okay, just greater than. So that tells me that my lower limit is not included. -4 is my lower limit. I don't have to write that. You might be tempted to write that, okay, y is less than infinity. You don't actually have to write that. If there's no upper limit, we just simply don't state it. Okay, so with set notation, if there's no limit, okay, then do not state, just do not state it. Okay, so if I don't show an upper limit, it means there is no upper limit. So I just leave it like that. Y is greater than -4, comma, y is a member of, go back to my number line, I see I have a solid line here, so that tells me that real numbers, it's continuous data. I'm only going to use integers, whole numbers, or natural numbers if I have data points. Okay, let's do this graph together because this is a good one. We did this graph before in the last lesson, so let's quickly look at the domain and range. Okay, the domain is my x values, and if I look along my x-axis, I see that there's my first point for x, the furthest point to the left, and the furthest point to the right will be right here. Okay, so my domain essentially goes from 0, okay, on my x-axis all the way to 4. Okay, so there's my domain. So let's start there. Okay, so the domain is 0 to 4, and those points are included. So in words, we would say that, right? So let's go ahead and show that with set notation. So curly brackets, x, because we're talking about domain, is such that the lower limit is 0, and that is a possible value because it's not an open data point. So I say x is greater than or equal to 0. It's less than or equal to 4, because that's the upper limit. And this is continuous data because I don't have just data points. They're all connected. And so I say x is a member of the real numbers. Curly bracket. Okay. Let's look at a range. So when I look at a range, I'm looking from the bottom to the top on my graph, and I look along the y-axis and I see that the very lowest point on my graph is down here. Okay, and on the y-axis that's at 0, and it goes all the way up to this point on my graph, and on my y-axis that's at y equals 2. Okay, and so that's my range. It goes from 0 to 2. So I would write that in set notation with a curly bracket. Y is such that y is greater than or equal to 0, less than or equal to 2, comma, y is a member of the real numbers. Close my brackets. Hopefully we're starting to get some good practice here. Let me just do a couple more with you that are one that is showing continuous data with no limits, and one for discrete data. Okay, let's have a look at this one. This is a great graph because lots of graphs don't have any upper or lower limits for many functions in math. We just have a graph like y is equal to x or something like that. And there's no limits, there's no restrictions on y or x. If we see a graph, we know there's no limits because we see these double arrows. So that arrow there tells me that there's no upper limit. And again, if you think about it, if you look at that graph, if you continued that graph on and on and on like this, it's getting higher for y, it's going in the positive direction for y, and it's also going in the positive direction for x as well. Okay, if I pick a point up here that's got a higher x value and a higher y value. So there's no upper limit for x or y. And down at the bottom I have another arrowhead, which tells me this is going in the negative direction for x, because it's going further to the right, and it's also going further down. So if I let this line continue, I see that it's coming down to an even lower value for y. So this is continuing in the negative direction for x or y. So there's no lower limit for x or y. So let's go ahead and say that then. Really, in other words, there's no limits. So no upper limit, no lower limits. It is continuous data because I have data points that are all connected. So I'm talking about real numbers. Okay, it's not that I can only have whole number coordinates or integer coordinates. These are any numbers on the line. So what I'm going to do here is describe my domain. And this is actually a really simple one to describe. We say the domain, curly brackets, x is such that, and we don't have any limits. There's no limits, so we don't state them. So let's write that up here. So when there's no limits, just like in the last example, there was no upper limit, so we didn't state it. When there's no limits, we don't state any limits then. So no limits, no need to state any limits. So that's middle part of the set notation where we usually say that x is greater than or less than something. We just leave it out. There's no limits. Okay, so we go straight to this. X is simply a member of the real numbers. This tells me that x can be anything, any real number, and there's no limits on x or y. Range is going to be the exact same thing here. There's no upper or lower limit for the y values, so we say curly bracket y is such that no limits, so we don't state them. Y is just a member of the real numbers. So these are actually really easy to write the domain and range for. There's no restrictions, is really what this means. No limits, no restrictions on x or y. You've got a little bit of room at the bottom of your notes. Let me just really quickly show you some discrete data because you might have to, we will run into some discrete data in this course. So let's just do one last example. Example 5, discrete data. I'm going to give you a number line. Actually, let me give you let's give you a list. So it could look like a number line or it could be a list, but actually, let's go ahead and do a number line. I'll make it a little easier for you. Okay, so domain. Let's say your domain is given as a number line. So your number line looks like this. Okay, here's your number line. Let's put 0 at the center. We'll go up 1, 2, 3, and we'll go back -1, -2, -3 like that. Okay, and let's go ahead and just put some data points on our number line. It would look like the same on a graph. It would look like data points. Let's say there's a data point at -2, -1, 0, 1, and 2. Okay, and let's say they're closed data points at all of them. The first thing that I notice is that they are not connected by a line. on my number line. So I know that this is not continuous data. The next thing I have to decide is it's discrete data. What kind of discrete data is it? Is it integers, whole numbers, or natural numbers? I see that I have negative values there, -2 and -1. So that tells me that I have integers. Okay, because your integers are the negative values and the positive counting numbers. Okay, so those are my integers. If -1, -2 were not on the number line, I could say they were whole numbers. But in this case, I have negative values, so I have to classify those numbers as integers. Okay, so let's go ahead and show the domain using set notation. Okay, so we're going to write a curly bracket and say x is such that, well, what's the lower limit of x? What's the lowest value I can have? It's -2. Okay, and x can go all the way up to +2. So that is, -2 is my lower limit, so I say x is greater than, and it can be equal to -2, and it's less than or equal to +2, which is my upper limit. So there's my lower limit. Okay, there's my upper limit. And I've been careful to use the right type of symbol, inequality symbol, to show that 2 as an upper limit is included and -2 is included. Now I just have to say what kind of numbers are these values. X is a member of the integers. So we use a capital I here. Okay, this is why set notation is so great, because it tells me that this is discrete data. It tells me that I can be any integer between -2 and 2. Okay, and so it gives me all the information I need. That's it for set notation. There's a worksheet I'd like you to try. It's in your worksheet package called 6.3 set notation. Check your answers. It gives you lots of practice with these. And then when you're done for this week. And we'll see you next class. Thanks for joining me. Bye for now.